In this video, we're going to look at the first of the rules for differentiation when we're looking at slightly more complicated expressions, because up to this point we've just been able to do expanded polynomials. So now we're going to look at how we can do things that are a little bit more complex, and this is called the chain rule. So I'm not going to go too much into the detail of the proof, but I will just show you how to use it and a couple of different ways that you can sort of notate it. So we know from our previous work with calculus that if we want to differentiate something like this, where we've got y equals x cubed plus 1 to the power of 2, then we can expand the brackets out and then just proceed as before, bring the power down, reduce by 1, and so on, which is fine when you've got a power of 2. Maybe okay for power of 3, starts getting a little bit painful when you're talking about a quartic. When you get up to something like to the power of 30, that's just going to be irritating. So we need another method of doing this. Luckily, we're going to have composite functions to the rescue. Okay, so the way we deal with this is by writing our polynomial, or whatever the function is, as a composite function. So I'm going to go back to the basic one, which we had, which was our x cubed plus 1. Now, we could do this, if we square that, we could do this by expanding it, but I'll show you how we're going to do this with composite functions. So the trick here is to split it into two functions where you're going to get things that you can differentiate quite easily. So for the first one, I'm going to say, well, let g of x equal, and I'm just going to pull out this bit in the bracket. So x cubed plus 1. And we're going to say, let f of x equal x squared. So you'll remember from our work of composite functions, if I say, what is f of g of x? Okay, g of x is this part, and f of x says x, we've got to square that. So we have our g of x, x cubed plus 1, squared, okay, which is our function up there. Okay, and what we can say is that q of x, so a new function, is f of g of x. So the chain rule states this, that if you've got q of x is f of g of x, like we had on the previous page, f of g of x, then the derivative of that function q of x, so that composite function, is the derivative of f of x, or f of g of x rather, so the derivative of f with respect to g of x, times the derivative of g with respect to x. Now, that looks particularly complicated and a little bit hard to get your head around, but once I do a couple of examples, you'll see what I mean. I won't go into the proof at this stage. We can prove it, and I can demonstrate the proof for anybody who's interested. But for the purposes of this course, you don't need to know the proof, you just need to know how to apply it. Okay, so basically what we're saying is the derivative of f with respect to g of x, and then the derivative of g with respect to x. So let's get straight to some examples, because that makes life a little bit easier. Okay, so the example here is y equals 4x cubed minus 5x all to the power of negative 2. Now I want to write that as a composite function, so I'm going to say let g of x equal, and I'm going to choose this bit inside the brackets. Now this is completely arbitrary. What you choose is up to you, but you'll learn that there's a bit of a knack to choosing something which then makes the differentiation easier. So typically, if you've got something in the brackets to a power, you let g of x equal whatever that is in the brackets, because I can differentiate that no problem. And if I have this term as my g of x, then I can differentiate that as well, as you'll see. Okay, so there we've got g of x. So I'm just going to differentiate that now. Alright, so bring this down, 12x squared minus 5. Alright, so that's my derivative there. I know that f of g of x is the same as g of x to the minus 2. I'm going to define it as such. So f of g of x is g of x to the minus 2. Okay, which means that f prime of g of x, so the derivative of f prime is basically the derivative of that as if this was the variable. So if you just pretend that whole thing in there is x, and then differentiate it as such, which means I bring the negative 2 down, multiplied by g of x, and reduce the power by 1. Okay, so I'm just sort of treating that g of x as I would if it was just an x. So if you had x to the minus 2, then you just bring that down, and just keeping that there. So then the derivative in total is the product of these two. Alright, because this is the derivative of f prime, so f prime of g of x, so negative 2 times g of x to the power of negative 3, times this one, the derivative of g with respect to x, 12x squared minus 5. Okay, and if I multiply that out, substitute g of x back into here and do a little bit of simplifying, I get minus 2, 12x squared minus 5, so that's those two, over, because of this negative here, 4x cubed, this is g of x, from back up the top there, to the power of 3. So I've just substituted this part, put it back in here, minus 2 comes from there, and the 12x squared minus 5 comes from here. Okay, so that's the derivative of this function here of y. So we can say that would be dy dx. Okay, now this composite function notation can get a little bit mucky, a little bit tricky to sort of try and get your head around. There's another notation called Leibniz notation, which of course comes from our dy dx, which is arguably easy to use because you end up with, well, less brackets for a start, and defining your functions is a little bit easier than defining them with composite. It's exactly the same thing, it's just a different way of looking at it, and it does seem to be a little bit easier for students to sort of get their head around. So I'll show you how to do exactly the same example, but we'll do it with Leibniz notation instead. So basically what it says is if you're trying to differentiate y with respect to x, and you can split it into two functions, y written in terms of u, and then u written in terms of x, and then differentiate each of them separately, and then multiply them. That will give you the same thing. It's exactly the same as doing it with the function notation, but it just seems to be a little bit clearer. So let's do the same example. Okay, so in this case, instead of saying we're going to let g of x equal whatever it was, we can say let u equal, and it's the same thing, picking the thing in brackets. Okay, and now from here, I need to do dy du, so differentiate y with respect to u, and differentiate u with respect to x. Okay, so y in terms of u is going to be u to the minus 2, okay, because we said that part there is u. Therefore, dy du is minus 2u to the minus 3. Okay, du dx, this is up here, so differentiating this with respect to x is our 12x squared minus 5. Therefore, dy by dx is this one, minus 2u to minus 3 times 12x squared minus 5. Okay, and that's the same, because then u substitutes back in, and that comes down the bottom, so minus 2, 12x squared minus 5 over 4x cubed minus 5x to the power of 3. So you can see the answer we get is exactly the same, but this notation just seems to be a little bit more straightforward rather than trying to muck around with f of g of x and remembering which one's which and what you're differentiating with respect to. Okay, so I tend to use the Leibniz notation much in preference to using your composite function notation, but it's of course entirely up to you. Alright, just a quick disclaimer on this one. Again, we're not going to go into differentiability in any great detail at the moment. We will cover that a little bit later in the course, but in order to use the chain rule, the following conditions must be satisfied. So g must be differentiable at x, and f must be differentiable at g of x. Okay, so that means at any point on that function, it must be, or the function that you're trying, the point that you're trying to differentiate at, both g and f of g of x must be differentiable. So you can't have any of those pointy bits or piecewise function or anything like that, asymptotes. Okay, but we will go into that in a little bit more detail further on in the course. Right, let's have a look at another example. So find the gradient of the tangent to the curve, which just means differentiate. Okay, find the gradient means differentiate, and we want to know what is the value when x equals 1. Okay, so part of this is deciphering the question, what's it actually asking you for. Okay, now this we don't really want to deal with at the moment. We've got variables on the bottom and it's sort of all a bit yucky, but if we say let u, so using my Leibniz notation, let u equal, and I'm going to say the whole part on the bottom, 3x squared plus 1, okay, then y will be 16 times u to the minus 1, okay, because of course this is to the power of minus 1 if we brought it up the top. Now I can differentiate dy du, so differentiating y with respect to u, negative 16 u, and of course that becomes negative 2, so reducing by 1. And if I differentiate u with respect to x, u dx, bring that down, 6x, of course that's just going to be 0, so just 6x. Therefore, dy dx is this, negative 16 to the minus 2 times this, which is 6x. Okay, and if I substitute that back in, I've got negative 16. I said u was this, 3x squared plus 1 squared times 6x. Okay, and I want to find out what is that when x equals 1. So I can simplify it and say, well, this is negative 96x over 3x squared plus 1 all squared. Okay, and then when x equals 1, I'm going to get dy dx is negative 96 times 1 over 3 times 1 squared plus 1 all squared, and that will give me negative 6. So the gradient of the tangent at the point x equals 1 is negative 6. It's quite a steep negative gradient there. Alright, one last equation, well, rather one last example. So this one's got some variables in it. So this is saying if you've got a linear equation to the power of anything, so polynomial to the power of anything, how do we differentiate that? Okay, so we can do the same thing using our substitution. I'm going to say let u equal the part in the brackets, the linear factor. Okay, therefore y equals u to the power of n. So dy du equals, now this is, we'll say n times u, and reduce this by 1, n minus 1. Okay, and du dx is just going to be a. Okay, and therefore dy dx is going to be this part, n times u to the n minus 1 times a. And if I substitute my u to the n minus 1 back in there, and then sort of rearrange a bit, we get a times n times ax plus b to the n minus 1. Okay, because we're saying that bit there is u. Alright, so that's just a general derivative there for any equation of this form here. So to use the chain rule, you want to write the function as a composite of two functions. And like I said before, it's a little bit of a knack deciding what function to choose. So when you say let u equal, deciding what to let u be is a little bit of a knack. But generally, if you've got anything on the bottom of a fraction, you use that whole expression. If you've got anything in the bracket to the power of something, you use the expression in the bracket. You'll get a feel for it as you do some more practice. You can use the composite function notation or the Leibniz. This is my preference for clarity. It just seems to be a lot easier to deal with. Okay, and remember that both functions must be differentiable at x for the composite function to be differentiable at x. Again, something we don't really cover in great detail in the methods course. Probably won't come up against it, but we will talk about differentiability in a little bit more detail a bit later on.